Welcome to the UEI Technical Master Class. I'm Bob Finn with UEI. I hope everyone here is doing well today. Today's webinar is entitled Analog Output Applications and Solutions. Our presenter today will be Timur Raza. In this masterclass, Timur will provide interesting insights into the analog output options you find in our UEI hardware. I want to remind everyone this is an interactive environment and we encourage you to ask questions. So if you've got a question, send it our way using the webinar chat tool. That wraps up my brief introduction. So without further ado, I'm going to hand this over to Timur. Take it away, Timur.
Hi, everyone. My name is Timur, and today I'll be talking about analog output. So I've put on screen our agenda for today. We'll start by talking about the digitization advantage, or the difference in the domains of digital and analog and how to leverage the best of both. And then we'll talk a little bit about 3 case studies where we apply the analog output, as well as a lot of other related concepts to various applications. So we have a feedback control system, a music generator, and a laser HUD. After that, we'll tie it all back to what an output can really be, as well as all of the AO options in UEI's catalog. All right, so let's start by talking about the digitization advantage. So the world, as we all know, is an analog place, right? The brakes on your car are analog. The music that you listen to is analog. Right? There are a lot of analog processes that we need to interact with in order to really make our lives better. Conversely, digital systems, I've got a photo of a PCB here to kind of stand in for that, are very easy to work with. They're simple, they're reconfigurable, and they open the door to a lot of modern day hardware that makes everything much easier. We've got stuff like the cloud, we've got IoT, which we covered in a previous application. We've got things like supercomputing and data centers. And these are all things that we should be able to leverage wherever we need them. So that kind of gets us to the UEI advantage. We provide ways to go easily between the 2 domains to leverage IoT and supercomputing and the cloud, but be able to apply that to the analog problems that we deal with today, or that you might deal with in your application at any time. So let's keep that in mind as we go through our 3 case studies for today. We first have a generic digital feedback control algorithm, or a system. We've got music generation and kind of the interesting things you can do with modifying the wave. And finally, we've got a laser HUD planned. This would be the kind of technology that you see in very new cars or jets and aircraft. All right, so let's start with our first case study, the feedback control loop. So we all know the kind of basic look of a feedback loop, and I've got it up top here. You've got your adder block, you've got a controller, and you've got the plant. We read back info from the plant and use that to adjust the output of our controller so that we can either overdamp, underdamp, or otherwise modify the characteristics of the output of our controller to basically achieve different characteristics. So what I've done here at the bottom is I've dropped in a UEI chassis, right? I've quote unquote digitized the system. In this case, the set point that we provide our adder block would just be a value we provide to our CPU. And we could use an analog output to supply an input to the plant and then read it back through an analog input. And at first, this might be kind of an arbitrary splitting hairs kind of distinction, but it's actually very powerful because our set point is now just a value, right? And because the input that we read back from the plant is just a value, we can adjust this digitally on the fly. If there are different algorithms or parameters that might make our plant output more accurate or faster, we can just download those from the cloud, or use whatever digital update scheme that you might prefer um, to improve your system digitally. And of course, this comes with a couple of other advantages as well. Normal feedback loops might take the form of a built PCB, right? You've got resistors and capacitors, and that builds up your feedback loop. However, adjusting the parameters of your loop might mean something as easy as tuning a potentiometer while it's on your desk, but that could potentially get more difficult if that device, for example, is out in the field with a customer, right? Do you figure out how to get that device back? Do you tune the potentiometer to be something else? Digitizing this process makes our lives much easier in a lot of different ways. Additionally, there's other things that we can do. For example, we can write certain adaptive digital algorithms and use that with our AO to also achieve different characteristics with the plant. So I guess what I'm getting at here is that this is kind of the most generic way to show the advantages of an analog output. And an analog output is easy to understand. So being able to apply it here kind of shows a lot of the advantages from a computational standpoint fairly directly. So now let's get into something a little bit more concrete. Music generation. And this is actually a very fun example to talk about. So earlier this week, I took a few scope captures to show a little bit more directly what I'm talking about. So the normal way we'd approach generating music would be the analog bit bang method, right? This is probably how a software engineer would approach this problem from a starting point. The image I have on the top left is a wave that I generated using the AO308. I picked 20 points along a sine wave, right, and just had the AO output them consecutively using a certain timing scheme. And as you can see, it's good. We get our waveform out, and we can, of course, smooth this out much more by using much more discrete points along the wave. However, the problem that we get into here is that we become timing constrained. If we want to generate certain riffs, for example, with a guitar or a drum, then we have to calculate those ahead of time. It becomes more difficult the more complex your wave is. So that kind of gets us into the next level of what an analog output can be, and that's a waveform generator. So our AO364 provides a whole lot of advantages and features that might make generating music much easier. The first is the arbitrary wave function generator, the AWFG. The idea is that you can provide a certain register with several values. You can preload a register with several values that the waveform generator can output consecutively. And this makes generating, for example, those riffs that I spoke about earlier, much easier because you've preloaded them, and you can have the waveform generator handle the exact details of outputting them at the right timing schemes. There's a couple of other advantages to using a waveform generator, though. We also provide frequency sweep, which is the oscilloscope capture on the bottom left. And this, again, would be very difficult if you were to use the analog bit bang method, because you'd have to calculate the exact point of the wave during the sweep. Our waveform generator can just do it natively. You can simply provide it the number of periods that you want to sweep over, and it'll handle the rest. And of course, for music, this is optimal, because if your song or whatever other sound you really want to generate has certain changes in frequency, or then implementing those changes becomes easier. Now, the last thing we can talk about with the waveform generator is clocking. So we actually have two different methods to clock the waves coming out of the AWFG. The first is DDS mode, and the second is PLL mode. So DDS is a direct digital synthesis method. The idea is that we use a digital process to generate pretty much any frequency that you need for most applications, right? The idea is that it's optimized for flexibility. Now, in the case of music, this might be ideal because songs are not static waves. They change, they modulate. So having that extra frequency in that particular mode might be advantageous. However, in other applications, getting away from music a little bit, PLL mode might be a little bit better. So PLL mode is our most precise mode. If you have a pretty standard frequency like 400 hertz or something that you need to output, but you need to output precisely and repeatedly, then you might use the PLL mode as it's more of an analog process and therefore more precise in terms of the feedback and the rise time and so on. All right, so now that we've talked a little bit about generating music with different modes, right, with different flexibilities and so on, let's talk about another application, our laser HUD. So on this slide here, I actually have a photo. This one's Commons, I believe, taken from a practice dogfight with an FA-18 Super Hornet. I think I have those details right. Might have to recheck them later. And the idea is that on screen, we've got a laser that draws an HUD that helps the pilot navigate and figure out exactly what is going on in his surroundings, his or her surroundings. And so that kind of leads us into how we would control such an HUD. That's also a very interesting set of control problems that we can optimize for. And again, this is an area where a waveform generator, our AO364, for example, really shines. So if we start by thinking about what we actually want to draw, we can get a little bit of a better idea about what the problem is. So if we want to simply draw lines, right, we might use a vector method where we trace the different things, the different shapes on screen, but we can't really do fill, we can't really do a grayscale either. The alternative to this is the raster method, right, where we sweep from left to right, top to bottom, and draw frames with our pointer, for example, every time. However, as you can probably guess, this is a much slower method. Deterministic, but your frame rate is limited. So if we jump back for a second and just take a look at this image again, we can guess that this is probably vectorized. Right, all of the numbers drawn on screen, the shapes and the navigation headings, they're all drawn in lines. There aren't really any filled in shapes. There isn't any grayscale image. So we can probably guess that because this needs to be a high-speed application, this would be something that's vectorized. And this is another thing that we can think about while implementing this with our 364. So from there, these types of devices are typically controlled using high-speed servos or galvo heads. I'm going to approach this from a high-speed servo perspective, using the X and Y servo micromirror motion method. The idea is that a servo in the X direction would shift a small mirror left and right, and then a servo for the Y direction would shift a small mirror up and down. And that angle would allow you to move around the laser very quickly. So as you can see, we need to generate multiple different PWM ratios. You might use a 50-25, as you can see in the first column here, to draw a certain point of that image. Or alternatively, if you wanted to vectorize it, you might use a different set of PWM duty cycles to draw that particular vector image. Now, what that's kind of leading us to is that our our 364 waveform generator can natively support these kinds of waves. We actually have built-in pulse mode. So on this oscilloscope capture on the right, I actually took this earlier in the week, showing duty cycles natively from the 364 that you might use to theoretically control this X and Y servo. So as you can see, all I needed to do, all I needed to do to generate these waves, right, this PWM wave, was simply input the duty cycle and set it to run. There wasn't very much difficult about timing it correctly. I simply needed to provide it what the parameters my application required, and I could get out this output. And of course, dynamically, you can change the duty cycle as your PWM application needs. So let's bring it all back together with kind of a talk about what an output really is. So up until now, in this part of the presentation, we've talked about how an output is a voltage. But we can actually output much more than that if we shift our thinking. An output can be a current source, and we provide that using our O2O and various other cards. And an output can also be a resistor, or an RTD, or an LVDT, as we spoke about in the previous masterclass. So all of that is to really say the analog output part of UEI's catalog isn't just outputting certain voltages, it's outputting a wide range of things that makes our lives easier, just in terms of the applications that we need to work with. So that brings us all the way back to UEI's analog output catalog, right? All of the options that we have. And I figured I'd just list them out, talk about them in a little bit of detail. And yeah, call that our master class. So our base AO variants can do both voltage and current, right? They're all 16-bit standard output, so you have nice smooth output waves. They're all 8 channels. Each of them is really tailored towards different applications. For example, the 4 to 20 milliamp or the 0 to 20 milliamp options can interface with certain current-based communication protocols, while the voltage output options are fairly generic and can be used for pretty much anything. We all, taking one step up, we have an isolated Guardian set of AO that can all do voltage and current readback. So in mission critical cases where you really need to make sure the output of our card is correct, you can always double check and check it in multiple different ways, as well as be sure that it's isolated from everything else in the system. We also have high density variants, we have source sync variants, and of course, the star of today's show, we have an arbitrary wave function generator variant as well. And kind of jumping back to what I talked about earlier, we also have simulator type AO. For example, if you wanted to output a strain gauge, if you wanted to take the characteristics of different RTDs or thermocouples, you can also do that using those 300 series boards. What is the typical AO range? Oh, we picked a great slide to end on, I guess. Right, so plus or minus 10 volts is the quote unquote normal range, but we have variants that can go up to 40 volts with plus or minus 40 volts with an external power supply. In terms of voltage, we can do 10 milliamps on the basic current output boards, but we can go up to 50 milliamps on the specialized ones. And I believe we can support all resistance ranges associated with any RTD using the RTD 388. If you're interested in that, definitely reach out for more details. Let's see. Oh, okay. This next question is about the feedback that we spoke about earlier. One moment, let me jump back to that slide so we can kind of go over it, so we can kind of be on the same page for it.
Timur, do you want to grab my slideshow again?
Yeah, sorry about that. I moved to the slideshow, but I didn't have it shared. All right, one moment. Let me share my screen. All right. Next question: how hard is it to implement a PID system? Sorry about that. Okay, so the answer to that is it depends. So PID system is actually pretty complex from a computational standpoint. The integral and derivative aspects of it or digitizing the integral and derivative aspects of it are kind of tough, but depending on your method, I think the difficulty in it depends on the method that you approach those two sections. Um, I'm sure you can use something with Simulink or LabVIEW as well. We have plugins for our systems in both of those development environments. So if you have like a model there that you want to use for a feedback control system, you can do that. Are features for the arbitrary wave function generator different across PAC and PowerDNA? The answer to that is no. Both versions get the full features available for the card. So you would get the frequency sweep, you would get the arbitrary wave function generation, sine wave generation, and pretty much anything you can do on PowerDNA, you can do on UEI PAC. Next question. Can I use framework for arbitrary wave function generation? I believe so, yes. Oh, a lot of control loop questions. Okay. Can I use my Python library, scikit or NumPy? NumPy? Never figure out how to say that out loud. I always have it written. To generate the info I need for my control loop. Yes, we recently added support for Python because we actually know that a lot of people are moving in that direction, that they have high precision applications that Python simply makes easier to do, more accessible. So yes, you should be able to do that. Okay, next question. Can I drive a speaker with an AO board? All right, that would be another it depends kind of question. It's definitely possible. I think that the main concern there is that because inductors have such a high inrush current, the main concern is ensuring that the board you selected can supply that current. Oh, looks like there's a follow-up to that one. Can I use an amplifier for current or voltage with your boards? And answer to that is yes, absolutely. I believe we actually supply a current buffer board as a starting point to kind of show that yes, you can amplify the output of an AO 308, I believe, or the output to any board. Our amplifier board specifically designed for the 308, but it worked with 364 as well. The point there being, you can use pretty much any amplifier depending on the characteristics you need out of that, depending on the power characteristics you need for your device. Oh, okay. Here's the next question. What happens in case there's a software/CPU glitch or brownout or other, let's say, failure mode? I guess the question here is what happens to the analog outputs. And under the hood, we actually have a watchdog running. So it should force all outputs to 0 volts as a safety precaution. So if that was something you were concerned about, right, if your application was a high precision or critical application, that's again, probably nothing to worry about.
Okay, thank you, Timur. That about concludes today's presentation. A few things to note. Our next masterclass will be August 20th, and it'll cover grounding and isolation solutions. We record every webinar and post the video online. You can find all of these archived masterclass videos on our YouTube page or on our own webpage, ueidaq.com/videos. And finally, if you've got an analog I/O question, you need additional support, or you've got a suggestion for future webinar topics, please email us at support@ueidaq.com or give us a call at 508-921-4600. We hope you found today's webinar useful, and we'll see you again on the 20th. Once again, thank you for joining us, and as always, please stay healthy.